If you've ever sat through a physics class and thought, I'm just not smart enough for this, stop. In November 1964, a 46-year-old physicist named Richard Feynman walked into a hall at Cornell, stood in front of 600 strangers, and said out loud, "Nobody really understands quantum mechanics." Then he taught it anyway. Last time on this channel, we followed his chalk through time. A positron, an electron making a U-turn. Today, we follow his chalk through space. One electron, two doors, at once. In the next 35 minutes, the man who won a Nobel Prize for not pretending to understand is going to explain it to you. And by the end, you'll know why the phone in your hand owes its existence to the thing he refused to pretend he understood. It is a Monday night in November 1964. A 46-year-old professor walks into a hall at Cornell University. 600 people are already seated. No slides. No notes. No safety net. Just a chalkboard, a piece of chalk, and a promise made to the BBC to record 6 evenings of lectures for the public. The series is called The Messenger Lectures. The man is Richard Feynman. He has, by this point, already helped build the atomic bomb. He will, 3 years later, share the Nobel Prize in Physics. He plays the bongos. He cracks safes. He teaches at Caltech. And tonight, he has decided to do something most physicists of his generation consider professionally reckless. He is going to explain quantum mechanics, the strangest, most successful, most unsettling theory in the history of science, to ordinary people, in plain English, without lying. He walks to the board. He picks up the chalk. He turns to face the room. I think I can safely say that nobody really understands quantum mechanics. Richard P. Feynman, Cornell University, 9, November 1964. The audience laughs. A short, uncertain laugh. The laugh of people who came for a physics lecture and are not sure if the famous man on stage is joking. He does not laugh back. He lets the silence sit. Do not keep saying to yourself, "But how can it be like that?" Because you will go down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. Now, stop. Because right now, watching this, something in you just tensed up. If the first thing you thought when Feynman said, "Nobody understands it," was, "So I can't understand it either?" I want you to hear me very clearly. That is not what he said. He did not say, "Go home, this isn't for you." He did not say, "Give up." He said something much more precise and much more generous. He said, "Nobody has a satisfying story for why the universe behaves this way." But he spent the next 5 evenings showing 600 strangers exactly how it behaves and exactly how to calculate it. Those are 2 different questions. And the second one, the how, is the one you are absolutely built to follow. So keep your hand on the chalk. We are going with him. That is the deal this video makes with you. For the next half an hour, we are going to follow the honest version of the story. The same story Feynman told that room at Cornell. And we are not going to pretend to know things we do not know. When we know how, we will show you how. When the answer is nobody knows why, We will say, nobody knows why, and keep moving. You came here because you have been lied to by confident people before. You will not be lied to tonight. So, before we walk into the strangest experiment in physics, let us remember what ordinary reality feels like. A rock is in your hand, or it is on the ground. A tennis ball goes through this door, or that door. Not both. A car arrives in the garage by one route. That is common sense. That is the physics that built cities, roads, bridges, cannons, and the entire Industrial Revolution. And for every object bigger than roughly a molecule, it is correct. But in 1801, a man named Thomas Young shines a light through two narrow slits, and the pattern on the wall looks like stripes. Interference stripes. Something only waves do. So light, we decide, is a wave. Then, in 1905, Einstein shows that the very same light, when it hits a metal plate, kicks electrons out in discrete lumps. Something only particles do. So light, we decide, is particles. Then, worse, in the 1920s, electrons, which everyone has been treating as obvious little bullets for 30 years, get fired through two slits, and they make stripes too. Like waves. And at that point, somewhere around 1927, a generation of physicists collectively took a breath and said, Okay, we do not get to pick one. They are not little balls. They are not ripples in a pond. They are something we have not yet named, that sometimes behaves like a ball, and sometimes behaves like a wave. And the thing that decides which behavior we see is, well, that is exactly what Feynman is about to show us. 3 thought experiments. Bullets. Water waves. Electrons. Hold on to those 3. We are going to walk through them, in that order, and by the end, you will see something the smartest people on Earth had to stop pretending was ordinary. 3 thought experiments. That is all we need. Bullets. Water waves. Electrons. If you can keep those 3 on one shelf for the next half hour, the rest of this video will feel less like a paradox and more like a logical walk. We are going to run each one at a time. No math. No jargon. Just watch what the detector says. Shelf 1. Bullets. Imagine a machine gun firing erratically at a wall with 2 holes in it. Behind the wall, a detector. Close hole 2. Fire for an hour. Count the hits. You get a single hump centered behind hole 1. Call that P1. Close hole 1. Do it again. You get a single hump behind hole 2. Call that P2. Open both holes. What do you see? You see P1 plus P2. 2 humps, smeared together. Common sense. Bullets are particles. Particles add up. Shelf 2. Water waves. Drop a paddle into a shallow pool. Waves roll out, hit a wall with 2 narrow slits, come out the other side, and overlap. The corks on the far wall do not make 2 humps. They make stripes. Tall, short, tall, short, tall. Where 2 crests meet, the cork jumps. Where a crest meets a trough, the cork barely moves at all. Interference. Waves do not add up. Waves interfere. Shelf 3. Electrons. Same setup. A source. 2 slits. A detector. But instead of bullets or waves, we fire electrons. Little bits of matter. The things your body is made of. Common sense says they should act like bullets. Two humps, P1 plus P2. Common sense says this is the easy case. Common sense is wrong. Electrons give us stripes. Like waves. Now things get strange. 4 words. That is the whole vocabulary. Word 1. Amplitude. Forget the textbook. Think of a wave on a pond. How strongly does the water push up? At a single point, at a single moment. That push, that upness, is the amplitude. A calm pond has small amplitude. A storm has large amplitude. Big wave, big amplitude. Small wave, small amplitude. That is all it is. How hard the wave pushes, at a point. Word 2. Probability. This one is the rule of the entire video. The chance of finding the electron at a point is the amplitude at that point. Squared. Multiply it by itself. That is it. Big amplitude, big chance. Small amplitude, small chance. Zero amplitude, zero chance. Memorize it or forget it. We'll remind you. Every time the detector clicks tonight, the reason it clicked in that spot and not another is the amplitude was bigger there, and we squared it. Word 3. Interference. Take 2 waves. Let them arrive at the same point, at the same time. 2 things can happen. 2 crests meet. They add taller wave, louder sound, brighter light. That is constructive interference. Or a crest meets a trough. They cancel. Flat water, silence, dark spot. That is destructive interference. Those alternating bright-dark stripes on the far wall of the water wave experiment, that is interference leaving its fingerprint. If you ever see stripes on a detector, something wave-like is happening. Write that down. Word 4. Wavefunction. And I am going to keep this one light, because physicists have been arguing about what it actually is for 100 years. For our purposes, a wave function is a way of bookkeeping. Before we look at the electron, the wave function keeps track of every place it could possibly be, and how strongly it could be there. It is the amplitude spread across space. It is not the electron. It is the ledger. When we measure the electron, the ledger collapses into a single entry. The electron shows up at one spot on the detector, and the probability of that spot is what the ledger said squared. That is as much as we need. Anyone who tells you more than that by minute 10 is selling you something. 3 shelves, 4 words, 1 experiment left. And what you are about to watch was Feynman's own answer to the question nobody else wanted to ask. The question that broke 300 years of common sense. The question that, if you answer it honestly, rewrites what the word reality is allowed to mean. Which slit did it go through? Which slit did it go through? Let us answer that honestly. Not the way a physics professor answers it. The way you and I would answer it if we walked into this lab tonight, cold, with nothing in our heads but common sense and the rule of the 3 shelves. We turn the gun down. Way down. So low that only 1 electron flies out at a time. Click. We wait. Click. Wait. Click. One electron. One click. One spot. Each electron shows up at exactly one place on the detector. Not a stripe. Not a smear. A point. Whatever else an electron is, when it arrives like a bullet. Like shelf 1. That is the behavior of a particle. So here is what any sane person would say. Call this Proposition A. Proposition A. Each electron goes through slit 1 or slit 2. One or the other. Not both. It is not a weird idea. It is the idea. Every electron is a tiny thing. Tiny things cannot be in two places at once. The detector clicks once per electron. So obviously, each electron picked a slit, traveled through it, and landed somewhere. If Proposition A is true, we can predict exactly what the detector will show us after an hour. Close slit 2. Fire for 10 minutes. We get hump 1, P1. Just like shelf 1 predicted. Close slit 1. Fire for 10 minutes. We get hump 2, P2. Open them both. If Proposition A is true, we should get P1 plus P2. 2 humps. Maybe a little filling in the middle where they overlap. Common sense. Bullets. Done. That is the prediction. That is the answer. That is what 9 out of 10 people watching this right now would write down, myself included, the first time I saw this experiment. And I want you to hold that answer in your hand for exactly 10 more seconds, because in 10 seconds we are going to open both slits. And the universe is going to make a fool of every person in the room. Both slits open. Fire. Hold on. Run that back. We fired electrons one at a time. Each electron showed up as a single click, in a single place, like a bullet. We fired 10,000 of them. And the places they chose to land, together, make the exact same stripes that water waves make. Not humps. Stripes. An interference pattern. The signature from section 5 of something wave-like. Bullets do not do this. Bullets, with 2 slits open, give you 2 humps. That is shelf 1. We drew it 5 minutes ago. You watched us draw it. Stripes mean waves. Stripes mean 2 paths, overlapping, interfering. But we were firing the electrons one at a time. There is only ever one electron in the room. What then is it interfering with? Let us test it. Pick a spot on the detector. Call it spot X. A dark stripe. A spot where, with both slits open, almost no electrons arrive. Now, close slit 2. Leave slit 1 open. Fire the gun again. 10,000 electrons. Count how many land at spot X. The answer is a lot more than almost none. Slit 1, by itself, sends plenty of electrons to spot X. Read that again. Closing slit 2, taking an option away, made more electrons land at X, not fewer. In ordinary life, if you close a door, you get fewer things coming through, not more. This is the paradox. Feynman walked 600 people through at Cornell. And there is only one way out of it. Each electron, it turns out, is not choosing a slit. Each electron is somehow going through both slits at the same time, and the two paths. The version that went left and the version that went right are interfering with each other, adding, canceling, making stripes. On the far wall, one electron, two paths, one detector click. A single clump of matter, doing something a single clump of matter is not allowed to do in shelf 1, in shelf 2, or in any kitchen, any garage, any universe you grew up believing in. Proposition A is dead. One or the other is dead. And the question now, the only question worth asking for the rest of this video, is, how is that possible? And when, exactly, does the electron choose one path over the other? So, if each electron is somehow going through both slits, and the two paths are interfering, then the obvious thing to do, the thing any curious person in the room would want to do, is to catch it in the act. Let us put a light right behind the slits. A simple light, the kind we already understand. If an electron passes through slit 1, the light scatters off it, and we see a tiny flash at slit 1. If it passes through slit 2, we see a flash at slit 2. Now we know. Now we catch it. Now the question, which slit did it go through, has an answer every single time. We turn on the light. We turn on the gun. We fire. Flash at slit 1. Flash at slit 2. Flash at slit 1. Flash at slit 1. Flash at slit 2. One electron, one flash, one slit. Clean. Lawful. Common sense. Restored. Proposition A, the one we buried in section 7, is starting to smell alive again. Maybe the electron really did go through one slit. Maybe all we had to do was look. And we look back at the detector at the far wall. Stripes are gone. Interference is gone. The stripes, the fingerprint of something wave-like, have evaporated. Two humps, the pattern of particles, the pattern of bullets. Your observation has changed the experimental result. And before your brain reaches for the mystical explanation, let me say this clearly, once. Observation here does not mean a human mind watching. It means a physical interaction that records which path information. A photon, a cloud chamber, a thermal vibration in the detector. Any of them will do. No consciousness required. No wizard in the room. What we did was fire light at the electron to see where it went. The light is not neutral. The light is physics. And the electron responded. Observation didn't disturb the electron. It informed the universe. That is the sentence. That is the whole thing. Read it again if you need to. I know. Hold on. Run that back. I had to sit with this one too. The moment we had information about which slit the electron went through, the stripes died. Not because our light was too bright. Not because our detector was too clumsy. Because the universe apparently keeps a ledger. When which slit is a question with an answer. Even an answer nobody has bothered to read. The universe treats the electron like a particle. When which slit is a question with no answer anywhere, the universe treats the electron like a wave. The rule is not about us. The rule is about the information. But we are not done. Because there is still a hatch in the logic, and an honest video has to open it. We dim the light. Way down. So dim that, sometimes, a single photon is not there to meet the electron at the slit. Sometimes the electron slips past and no flash fires. So now we have three kinds of events. Flash at slit 1. Flash at slit 2. And no flash at all. We sort the electrons by bucket. And we build three separate detector patterns. One pattern for each bucket. Bucket 1. Flash at slit 1. Pattern, a single hump behind slit 1. Bullets. Classical. Boring. Bucket 2. Flash at slit 2. Pattern, a single hump behind slit 2. Bullets. Classical. Boring. Bucket 3. No flash. Which means no information. Which means nobody in the universe, not us, not our detector, not the dimmed light, knows which slit that electron went through. The pattern in bucket 3 is stripes. Full interference. Back. Exactly. As if the light had never been turned on at all. This is not about disturbance. It is about information. And I want to be precise about what information means here, because this is where bad science writing drifts into magic. Information, in this experiment, is not a thought. It is not a feeling. It is a physical record. A photon that did or did not scatter. A molecule that did or did not vibrate. A state that did or did not change somewhere in the world. The universe does not care who reads the record. It only cares whether the record exists. If the record exists, the electron behaves like a particle. If no record exists anywhere, the electron behaves like a wave. That is the rule. Hold on to this sentence. I am going to ask you to remember it for exactly the next 10 minutes. Nature treats information about which path as a physical variable. Because in Act 3, when we walk out of this lab and into your pocket, we are going to see that this exact principle, the difference between measurable and not measurable, is the only reason your phone turns on in the morning. Your phone's processor. Its memory. Its encryption. Every transistor is a small, fast, quiet referendum on the line we just drew. Promise made. 10 minutes. Hold. One last cleanup, because you are about to feel a very reasonable objection, and I want to meet it before you have to raise it. If every particle in your body is following this rule, why do you not feel wave-like? Why can you not walk through 2 doors at once? The honest answer is, because your body is warm, and warm means your molecules are constantly bumping into each other, and every one of those bumps is a tiny observation. In your body, the interference collapses in femtoseconds, trillionths of a second. You are a very effective detector of yourself. But the underlying rule is the same. And in certain quantum-protected systems, photosynthesis in a leaf, a robin navigating by the Earth's magnetic field, an enzyme catalyzing a reaction. Physicists have now measured interference lasting long enough to matter biologically. The rule does not stop at the laboratory door. One more dial to turn. The light behind the slits is not just bright or dim. It has a color, a wavelength, and wavelength matters. Short wavelength, sharp flash. We can tell which slit it was. long wavelength, blurry flash. The spot of light is bigger than the gap between the slits. We genuinely cannot tell which slit the electron used. Perfect distinguishability. Zero interference. Zero distinguishability. Full interference. Partial. Partial. A continuous gradient. No knobs hidden behind a curtain. No mysticism. The universe does not round. It measures. Everything we just watched. The stripes dying, the dimmer light buckets, the wavelength slider. Has a name. One name. It was written down in nearly its current form by a 25-year-old physicist named Werner Heisenberg in March 1927 in a single-room apartment in Copenhagen over roughly 10 sleepless days. And the name, in English, is the uncertainty principle. Here it is, in one sentence. The only sentence from this video you ever need to memorize. The more precisely you pin down where a particle is, the less precisely the universe allows you to know how fast it is going. And the reverse is also true. Not because your instrument is clumsy. Not because your eyes are bad. Because, at the scale of an electron, where and how fast are not two separate facts the universe is hiding from you. They are two readings off the same ledger. The ledger we called the Wavefunction in Section 5. And the ledger itself forbids both readings from ever being sharp at the same time. That is not a rule about us. That is a rule about the ledger. And here is the part that makes it a law, and not an opinion. Deltax, deltap, is greater than or equal to 2. Uncertainty in where times uncertainty in how fast is never smaller than a fixed number. That fixed number, h bar over 2, has been measured in laboratories from Boulder to Paris to 11 decimal places. It is the smallest possible trade the universe will ever let you make between the two readings. Smaller than an atom. Smaller than a thought. But non-zero. And because it is non-zero, the whole experiment we just ran, the two slits, the stripes, the flashes, could not have come out any other way. It is not. Our instruments are too weak. It is. The universe itself enforces a minimum trade. Read that again, because most of the internet gets this one backwards. I am going to say the Feynman honest version of all of this in one breath, because you earned it. Nobody knows why the universe enforces this trade. Heisenberg did not know. Feynman did not know. The physicists running the experiment this morning, somewhere in a basement at Delft, do not know. We only know that it does. And we have measured that it does, to 1 part in a billion, in every lab that has ever tried to make it not. And that is the end of Act 2. We had a question at minute 10. Which slit did it go through? And we now have an answer. The answer is, the question itself, in this universe, does not always have a value. Until something in the world records it. Before we walk out of the Cornell lab and into your pocket, one honest beat, because I owe you one. You are in 2026. You have been watching explainer videos for a decade. Somewhere around 2023, a lot of them stopped being made by people. I am not going to pretend this one is AI-free, and I am not going to pretend it is AI-made. It is neither. So here is the receipt. 1. Every physics claim in this video was cross-checked against the original Messenger lectures, Feynman's lectures on Physics Volume 3, and 3 peer-reviewed papers from 2007, 2013, and 2000 and 21, all linked in the pinned comment. 2. The visual animations for the two-slit experiment, the wavelength slider, and the interference patterns were scripted, frame-counted, and approved by a human physicist before render. The model was used as a drafting tool, not as a referee. 3. Every sentence in this script was rewritten by hand at least twice. AI did not write the final version of any line you have heard in the last 27 minutes. It suggested. I decided. 4. If you find an error, say so in the comments. I will pin the correction under my name within 48 hours. That is the standard Feynman kept at Caltech, and it is the standard this channel keeps in 2026. That is the promise from Section 2, scaled for the current year. You will not be lied to tonight only means something if I tell you how I could have lied and didn't. And now, with that on the table, let us walk out of Cornell. And into your pocket. We left Cornell in November 1964. But to understand what Feynman actually did with this paradox, the uncertainty principle just named for us, we have to go 16 years earlier and roughly 300 miles southeast. Spring 1948. A hotel in Pennsylvania. 28 physicists behind closed doors, arguing about what to do with the wreckage quantum mechanics had left on the floor. And a 30-year-old Richard Feynman stands up, goes to the chalkboard, and offers them a reframe that, at first, most of them hate. It is the reframe that, 20 years later, wins him the Nobel Prize. And it is the cleanest way for you to walk out of this video holding the paradox without dropping it. Here's what he said, and I am going to say it the way he would have. No math, one sentence. It takes every path, all at once, and then we add up the clocks. Let me unpack that. We said at minute 5 that shelf 3, electrons, give stripes even when fired one at a time. And at minute 15, we said each electron goes through both slits. Feynman's reframe is, both slits is not the whole story. One electron, fired at 2 slits, does not just go through slit 1 and slit 2. It also goes through slit 1 twice. It goes through slit 2 and loops back. It goes through slit 1, over the top of the apparatus, and down through slit 2. It goes every possible way. And on each possible way, the electron carries a tiny clock. The clock on each path rotates as the electron travels. Different paths take different times. So different clocks land on the detector pointing in different directions. Some point up, some point down, some point sideways. And then, and this is the whole trick, we add the arrows. Tip to tail. Like vectors. Like a treasure hunt. 5 paces north, 3 paces east, 2 paces south. Wherever we end up, that length, squared, is the probability the electron arrives at that spot on the detector. Long arrow, big probability, bright stripe. Short arrow, tiny probability, dark stripe. That is where the stripes come from. Not from magic. From arithmetic on a few billion clocks. And here is the part that made the older physicists in that Pennsylvania hotel go quiet. If you do this for a large, ordinary object, a baseball, a bullet, your coffee cup, almost every possible path's clock cancels. Almost every other possible path's clock. Total chaos, except around one thin ribbon of paths. The straight line from where the object was to where Newton said it would go. That is where classical physics comes from. Newton's laws are not separate rules. They are what is left when the clocks of a trillion quantum paths cancel each other out and leave behind one narrow survivor. The universe is quantum all the way down. We just happen to live at a scale where the cancellation is complete. One more honest beat, because you earned it. Before Feynman, 1927, 1947, quantum mechanics works, but nobody can picture why. After Feynman, 1948, add up the clocks on every path. Squared. Done. This method, sum over paths, is the same method used today to design the transistor in your phone, the laser in your supermarket scanner, the MRI that imaged your grandmother's knee. And it matches experimental measurement across every one of those applications to roughly 1 part in a trillion. 1 part in a trillion. That is not it mostly works. That is the best agreement between a human theory and physical reality in the history of science. And we earned it by not pretending. 10 minutes ago, I asked you to hold on to one sentence. Nature treats information about which path as a physical variable. Here is why. Take your phone out of your pocket. Look at it. 4 receipts. Receipt 1, the processor. Your phone has roughly 15 billion transistors. Each one is a gate that lets electrons through, or doesn't, based on a small applied voltage. At the scale those gates operate today, around 2 nanometers, electrons do not always respect the gate. They tunnel. They quantum mechanically show up on the far side through a wall that, classically, should be impassable. Chip designers do not fight this. They engineer around it. Every phone built since roughly 2015 is a machine that works only because we accepted Section 8's rule. Receipt 2, the laser. Every laser, the scanner at the grocery, the pointer at a meeting, the pulse of light carrying this video from a data center to you, works by stimulated emission. Einstein predicted stimulated emission in 1917 from the same quantization rules that force Section 8's interference. 1960, Theodore Maiman builds the first working one. Today, that single prediction carries roughly 99% of international internet traffic. Receipt 3, GPS. Every GPS satellite carries an atomic clock. That clock runs on a hyperfine quantum transition in a cesium atom. The same kind of transition the uncertainty principle governs. Without relativity and quantum precision corrections, your map on your phone would drift roughly 11 kilometers per day, every day, forever. Your Uber would show up in a different neighborhood, every single day. The fact that your Uber shows up at your door is a daily experimental confirmation of Section 8's rule, Section 10's formula, and Section 12's method. Receipt 4, MRI. MRI images your body by flipping nuclear spin states. Quantized, 2-level, exactly the kind of discrete outcome Section 8 demanded. Every MRI scan taken since 1977 is a direct reading of the ledger. Your pocket is a receipt. Your grocery scanner is a receipt. Your map is a receipt. Your grandmother's knee scan is a receipt. The thing Feynman refused to pretend to understand in a hall in 1964, the thing 600 strangers laughed nervously at, is right now running the civilization you are sitting inside of. Here is the thing I want you to leave with. You are not a classical object with quantum parts inside it. You are the thing Section 12 showed us. A quantum system where almost every possible path's clock cancels almost every other path's clock. And what is left over? The narrow ribbon that survives is the life you call ordinary. Ordinary is what the universe hands you after it has done the arithmetic. And now, when you look at your phone, you know what is happening underneath the glass. You know what Feynman refused to pretend to understand. And you know why he refused to pretend. Remember the 3 shelves. Bullets. Add up. Humps. Particles. Water waves. Interfere. Stripes. Paths. Electrons. Do both. Whichever the universe has a record of, it gives you. That is the whole video on 3 shelves. A thing is what the universe has a record of it being. Take a breath. Read that sentence again later, when you put the phone down. I want to tell you one more thing before we close. An electron knows if you're watching it. Not because it is conscious. Because the universe keeps a record, and a thing is what the universe has a record of it being. You walked into this video 35 minutes ago and somebody, somewhere, had told you that quantum mechanics was not for you. Tonight you followed Feynman's chalk through Bailey Hall, through Copenhagen, through Pocono, and into your own pocket. You now know things almost nobody you know can explain. Keep that. 2 small requests, and then I will let you go. 1. If this video earned its 35 minutes, subscribe. That is the only signal I trust that tells me to keep making the long version of the story instead of the short one. 2. If one receipt surprised you, the transistor, the laser, the GPS, the MRI, drop the word in the comments. I read everyone. And if you caught an error anywhere in the last 35 minutes, write it there too. I will pin the correction under my name within 48 hours. Same standard as Section 11. Same standard Feynman kept at Caltech. Next on this channel. In video 12, we followed Feynman's chalk through time. In video 13, tonight, through space. In video 14, we follow it through something that is neither. A single photon, split in 2, traveling to 2 detectors a universe apart, and somehow still knowing about each other the moment one of them is measured. Entanglement. Same chalk. Same man. Same honesty. Until then, keep your hand on the chalk. Ugh.